Now let's look at sum of squares as an example. In this case, we have this problem where, given a number n, we want to see whether n is going to be the sum of two squares. So 25, for example, is the sum of 16 plus 9, which is the sum of 4 squared plus 3 squared, to give us 5 squared, or 25. So there are many different ways of solving this problem because the algorithm is quite straightforward to explain, but actually if we examine the efficiency of this problem, we can see that there are many different interesting ways to go about doing it. So now let's run through that here. So I'm gonna paste it all inside Sublime and let's run through different functions. So the first one, f1, solves this problem by going through it in the most straightforward way. It starts from 0 and goes up to n inclusive, so let's say 0 to 25 for a first value of x, and then loops through the same exact corresponding pair for y, going from 0 to 25, and sees whether or not any of these squares of pairs can add up to the total n. So therefore, once it finds a true case, it returns true right away. The efficiency of this f1 function is going to be the outer loop here, so it goes from 0 to n, which could be some large number n, so we're going to call it O of n, and then the second loop also is O of n. So two nested O of n loops will give us O of n squared. So f1 is going to have an O of n squared runtime, which is seen from these two nested for loops. Now we have f2. f2 solves it in a little cleverer way because it recognizes that in a sum of squares pair, you have one value that's going to be less than or equal to the other value. So 3 squared plus 4 squared is 25. So 3 is less than 4. Therefore, it only recognizes that you can start from the base pair x in the while loop. So then it goes from x to the ending inclusive value of n. So in this case, we have O of n, and then this is going to be O of n minus some constant value, but in 112 terms, we're going to call that O of n as well. So this function is also going to be O of n squared. O of n squared. So now the third way, f3, solves this by recognizing that the problem spec is to look for the sum of squares. So therefore, you only really need to check up to a maximum value of the square root of n. Because, for example, 25 is never going to be equal to 25 squared plus something else. So therefore, it recognizes this cap, and then goes only up to the cap, starting from 0 to x max. And finally, it also recognizes to start from your starting value x, and then yet again go up to the max value of n inclusive. So this is going to be the square root of n times O of n. So this is going to be O of n to the 3 halves. O of n to, I guess 1.5, I'm going to call it that. So this is because we have an O of n plus O of square root of n times an O of n loop right here. And our next solution recognizes this cleverer one where you don't have to go up to n inclusive because there clearly is no solution past the square root of n in any case. Otherwise, you're just going to surpass your wanted case. So therefore, this is going to be square root of n times square root of n, which is O of n, right? So in that case, it knows to stop as soon as it reaches this max. Therefore, if we have something like 24, which is not the sum of squares, it stops right after the square root of 24, rather than trying to find true cases for 23 squared plus something else. So therefore, this is going to be a much different way, different function family group than the ones that we previously saw. And the last method is the most clever of all, because it starts off by recognizing the cap at x max, for both actually x and y, which is why it's called x and y max. And then it actually solves for a potential solution by taking the differences of the target value minus the square of the first solution, x, and then taking the square root of that and making that an integer, and then checking to see if the sum of the squares of x plus this potential solution y is equal to n. So this is nice because you know you have to go through O of n to the 1/2, but then this right here is constant time because you're just performing mathematical operations on constants, n and x, which are fixed for that time being, or x's, and then this is also a mathematical operation. So therefore this whole function f5 takes O of n to the 1/2 time, which lands it into a much different function family than what we previously saw. So therefore we can test these different function families by running timer functions. You can look through this yourself. We're going to first verify that these f1 to f5 actually do solve the problem by going from numbers 0 to 100 or 0 to 99, and making sure that we return true and false as needed. Finally, we're going to call a timer function by starting it. This is just a way that we can return a nice millisecond unit, and we can just take a difference between starting and end times to return the actual time that it took to run a certain function that got a certain argument and that we give it. So now we have a timer function call that calls all the functions in a list f1 to f5, gives it a certain parameter that we can say is 1001 to begin with. So it says, hey, I want to see whether 1001 gives me true or false to be a sum of squares, and tell me how long it takes as well. We can build it, and we can see that those values do return true, so these functions work. They solve the problem correctly. At this point, it's kind of hard to see whether or not f1 and f2, and even maybe f3, are super different, so in terms of efficiency. So now we're going to, let's say, change it to 3000, as the recommendation goes, and then we can see how different they are, really, truly. So it should be running because it took me not this long to run. There we go. So these functions take very, very long. Yeah, so we can see a significant difference within f5 and f4, and this is because this is a square root of n, this is O of n. This is actually a little harder to see, but if we run it from maybe like 2001, I think this is what I had before as a test case. Yeah, then we can see that it's significantly different between f3 and f4, and then f3 and f5, or then f4 and f5, of course, because you significantly change your algorithm by going and starting at different points. So the point of this is to understand that to solve a problem, there also is the problem of efficiency, which we have now just started covering in 112 and with this sum of squares example.